Hello everyone. So, we were discussing regarding the basic steam power cycle. The ideal cycle for steam power plant is the Rankine cycle, and already I have shown the physical arrangement of Rankine cycle with 4 basic component: boiler, turbine, condenser and feed pump. Then I have shown the Rankine cycle on a TS plane, thermodynamic plane. So, what we can do, what is done very routinely, that we can determine the efficiency of the Rankine cycle. Eta Rankine assuming that all the processes are ideal process, then from the basic definition this is W net divided by Q boiler. So, this can be written as W turbine minus W pump divided by Q boiler. So, this again can be written as turbine work, that can be assuming turbine to be a device which is operating under a steady state steady flow condition, and also assuming that the changes in kinetic and potential energies are minimum, there is no loss from the turbine. One can write that turbine work is given by the enthalpy difference, that means H 1 minus H 2, this is the specific enthalpy of steam expanding through the turbine. So, this is your turbine work minus W pump. The pump work is little bit tricky to determine, because you see the pump the starting point where the or entry point to the pump, that is 3, where the liquid is in the saturated liquid condition. The condensate is at saturated liquid condition, but when the water is pressurized, it is in the subcooled liquid region. Subcooled liquid region properties are not easily available. Conventionally, we determine the property using a steam table. So, H 4 is not easily available in steam table. So, what we do, we think of that it is work done by a device, steady flow device again, and this work done neglecting all kind of losses etc. It is some sort of a incompressible fluid which is pressurized. So, work done can be written approximately as V 3 into delta P. So, delta P, let me write somewhere over here, delta P is P boiler minus P condenser. So, basically the pump is raising the pressure from the condenser, raising the pressure of the fluid from the condenser pressure to the boiler pressure. So, delta P is this one, and then what is the heat transfer in the boiler? Heat transfer in the boiler should be given by H 1 minus H 4. Again H 4 is difficult to determine. So, one can write H 1 minus H 2 minus V 3 delta P. H 4, that can be written as H 3. H 3 can be easily calculated or looked from a steam table, property table. This plus the pump work that has gone. So, one can write H 1 minus H 3 plus V 3 delta P. Now, for most of the or many of the steam power cycle, the pump work is very small compared to other energy terms. Of course, this need not be true for steam power cycle where the boiler pressure is very high. Now, assuming that pump work is negligibly small compared to other terms, so one can write it is equal to H 1 minus H 2 divided by H 1 minus H 3. So, all the values can be readily obtained from some sort of a property table, or nowadays one can use some sort of engineering equation solver, and then knowing the boiler pressure and condenser pressure and knowing the degree of superheat at the entry of the turbine, one can determine the efficiency of the cycle, of the Rankine cycle. So, then once we determine the efficiency of the Rankine cycle, so we are in a position to find out how much thermal energy we are converting into work. And then also again if we take a critical look, then we can think of whether or what are the possibilities of increasing this conversion. With this, let us proceed with this basic idea. Now, what I like to discuss at this moment, that the basic cycle which we have shown, which I have shown, and whose performance parameter, that means the efficiency we have determined, that is an ideal cycle. So, there are many places where the cycle, the actual cycle will deviate from the ideal cycle. There are many places where there are irreversibilities. Let us have a quick discussion on those points, and then let us see how we can modify the cycle, so that we can have a better conversion of energy. First, let us look into the irreversibilities of the cycle. Irreversibilities in Rankine cycle. The irreversibilities we can divide into the figure which I have shown is a reversible cycle or ideal cycle. There will be different kind of irreversibilities, and the irreversibilities we can divide into two categories. There will be internal irreversibility, there will be external irreversibility. Internal irreversibility, of course, that will come due to friction, due to kind of expansion in some places, due to pipeline losses, etc. So, those things will come, and that will give some sort of a lower performance, that will create a deterioration of performance of the cycle. But two devices which will give which are of particular concern is that if you see, we have taken the expansion process and the compression process of the fluid, that is expansion process is in the turbine and compression process is in the pump, pressure rise process of pressure rise. These are we have taken reversible adiabatic or isentropic process. Now, it does not happen. So, in case of turbine, there will be some sort of loss, and due to the loss, So, exit of turbine will move somewhere over here. In the pump also there will be certain amount of loss, and the exit of pump, the exit point of pump will move somewhere over here. Now, these two losses are generally considered by introducing some isentropic efficiency of these devices. For both for the pump and turbine, we introduce some sort of isentropic efficiency. There would be some sort of a pressure loss in the piping. So, the boiler pressure, whatever boiler pressure we get at the exit of the pump, the same pressure will not remain. There will be some heat losses in the piping, etc. So, those kind of losses are there, but let us look into the external irreversibilities, which are very important and which are also important from the waste heat recovery point of view. So, for that we have to look into the heating and cooling process of the cycle. So, heating and cooling process of the cycle, if we look into, let us have the heating process. External irreversibility. So, heating process. So, how the working fluid is heated? So, in a boiler there will be combustion and fuel will be burnt, and the hot flue gas that will exchange heat to the working fluid, so that the temperature of the working fluid will increase. So, you see, if this is your thermodynamic plane T and S, this is the path of the hot flue gas, or this is how the hot flue gas gets cooled, and then this is how your working fluid changes its temperature. So, this part is economizer, this is your evaporator, and this is your superheater. This is the superheater. Now, here you see we have shown more or less a counter current flow type of these arrows will be in the opposite direction, sorry about that, these arrows will be in the opposite direction, okay. Counter current type of arrangement. Let me put another arrow to avoid any ambiguity. So, here you see one thing you have to remember when we have discussed the thermodynamic principles, then we have told that heat transfer across a finite temperature difference causes irreversibility. So, here what we can see that there is a difference between the temperature at any location, there is a difference between the temperature of the flue gas and the temperature of the working fluid. In fact, that is essential, because unless that temperature difference is there, no heat transfer will take place. So, temperature difference is needed for heat transfer, but at the same time it also creates some sort of irreversibility. So, always there is a tendency, or this is lookout of the engineers, to have a good heat exchanger or good device which will allow heat transfer between these two streams while keeping the temperature difference between them the minimum. Now, what we like to do? We like to bring these two curves closer. One curve is for flue gas, this is for flue gas, or hot product of combustion, and this is for steam. So, we want to bring them closer. Now, if we try to bring them closer, so this point will be the closest, and this point is known as pinch point. So, this becomes the determining factor that how close we can bring these two curves. The lowest the pinch point, the lower the pinch point rather, the more difficult will be to transfer heat, and more costly will be the equipment in which this heat transfer is taking place. So, there is a limitation from the pinch point, and that determines what will be the external irreversibility in this case. This pinch point is a very unique point, and particularly it is very important when there is a process like this where partially it is single phase heating, then it is phase change, and then again single phase heating, and we will see its further implication when we will proceed. If we see the cooling process, so this is for the heating process. If we see the cooling process, let us draw it in this page itself. So, this is for the heating process. So, for the heating process we have got this diagram. This is now, if we see the cooling process, then again we can think of let us take another page. So, cooling process. Cooling process, the steam is, this is the two phase dome, this is how the steam is getting condensed or getting cooled, and then in a condenser how the steam is cooled? It is cooled due to its transfer of heat to the circulating water. So, the circulating water will have supply of heat from the condensing steam, and the circulating water will have a change in temperature depicted by this blue line. So, this side is again T and this side is S. So, here also the same principle applies, that if we can bring these two curves together, close together, then we will have lesser amount of irreversibility. And here you see this point becomes the determining factor, and this is called, for a heat exchanger, this is called TTD. TTD is terminal temperature difference. Terminal temperature difference. So, for a heat exchanger there is a terminal temperature difference. We cannot go beyond this terminal temperature difference. If we go for a lower terminal temperature difference, generally either the heat exchanger size or the design of the heat exchanger has to be changed, and there is a cost implication. So, you see that terminal temperature difference cannot be made equal to 0, and that is why there will be certain amount of external irreversibility. So, both we have discussed regarding some internal irreversibility and external irreversibility, and basically these are losses. Due to losses we will have this kind of irreversibilities. That means, what I mean to say, the lowest temperature which would have been ideally possible will not be achievable in this case due to the restriction of pinch point, and in this case it would not be achieved. In case of condenser, it will not be achieved due to the terminal temperature difference. So, you see, due to the inherent limitation of the process, achieving maximum cycle temperature is restricted, and achieving minimum cycle temperature, that is also restricted. So, from ideal cycle, these are the 2 points which makes it less efficient. The practical cycle will be less efficient for these 2 points, for these 2 issues which I have discussed. More than that, I have discussed 2 other things, that there will be losses during the expansion process in the turbine and during the compression process in the pump. Generally, the pump energy consumption is less, pump losses are also less. That may not be a very serious concern, but the turbine losses could be significant. So, what we can see from this discussion? From this discussion, it is clear that whatever ideal cycle efficiency we have derived, in actual practice we are not going to get that. So, if we are not going to get that, we have to do something, we have to modify the cycle in such a way, so that we gain somewhere to compensate this kind of losses. So, there are certain variation of design, certain modification or improvement of design for the Rankine cycle, and very quickly I like to go through those kind of variation, design variation. The first design variation which one can think of, that is called reheat cycle. So, reheat cycle, it is something like this. We have got the boiler, from the boiler we are having the steam in the boiler that goes to the turbine, expands, and obviously the energy of the steam that is used for producing work, and this steam, this low energy steam, now what I can do, I can bring it back to the boiler, heat it once again, send it to a low pressure turbine to do some more work, and then this steam is taken to the condenser. Then there is a feed pump and sent to boiler. So, this is what is the arrangement for a reheat cycle. Again, if we denote these points, this is 1. After the high pressure expansion in the first turbine, it is 2, it goes to the boiler. So, when it comes, its condition is 3, it goes to the low pressure turbine and then it comes out after expansion, this is 4, after this condenser it is 5 and then it goes to the feed pump, it is 6. Then it goes to the boiler again and superheated steam is supplied to the high pressure boiler. So, now the cycle diagram which we will get is like this. Again in TS plane we will have this kind of a cycle diagram. So, let us put the point 1 to 2 expansion, then 2 to 3 that is heating, 3 to 4 further expansion in low pressure turbine, then 4 to 5 is condensation, then 5 to 6 that is pressure rise in the pump and then 6 to 1 again heating in the boiler. So, you see heat addition is there at 2 places. This is the usual heat addition process which we have seen in the first case also and in the second case there is additional heat addition when this steam is reheated. And very quickly one can calculate the work done. Let us say this is turbine 1, this is turbine 2 and one can have that efficiency of Rankine with reheat that is one can take both the work. The first work will be H 1 minus H 2, work by the second turbine that will be H 3 minus H 4. This from this the pump work W pump has to be deducted, because in this kind of cycle generally the pressure level is high, boiler pressure is high and pump work in most of the cases it is better not to neglect. And then there is heat given by the boiler. So, that is H 1 minus H 6 plus again heat given by the boiler due to reheat for reheating. So, this is H 3 minus H 2. So, what we get that using the same amount of working fluid we get some more amount of work out of the same plant. This is a good principle of energy conversion, but as far as efficiency of the cycle is concerned, one cannot definitely say that it will increase the efficiency of the cycle. Definitely it increases the work output of the cycle, but regarding efficiency one cannot definitely say anything. There could be some increase, some slight increase in efficiency. But this is a good principle. In most of the utility power plant this reheat cycle is used. Reheat cycle has got another advantage which I like to point out, the exit steam that is very dry. Okay. Without reheat we could have got the exit stream over here which is wet steam and not good for turbine. So, here it is quite dry and good for the turbine. So, this is another benefit, added benefit for reheat cycle. Generally these two temperatures are kept at the same level this 1 and 3 are more or less at the same level because of material constraint. We keep these two temperatures almost at the same level. So, this is your reheat cycle. It has got advantage in giving more power for almost the same kind of plant size. Of course, in certain places the plant size will increase, but that is minimal. There are other modification which we will go into the coming classes, coming lecture we will discuss about it. Many of you have are familiar with this kind of variation of Rankine cycle, basic Rankine cycle etc. But we assume that the participants have come from varied background, that is why we are quickly trying to have a recap. So, with this I like to end today's lecture. Thank you, and next lecture we will continue with further modification of Rankine cycle.